So this is one type of visualization that we could use to address the issue that just showing the marginal confidence intervals doesn't always lead to the right answer. Again, just a recap of the motivation as we discussed at the start of the talk. Having overlap of the marginal confidence intervals doesn't necessarily mean that things are not significantly different. Having non-overlap also doesn't necessarily mean that they are significantly different. So we're going to try and visualize these things directly. The ranking table itself showed the significance of differences. That's all it shows. It doesn't have the intervals plotted on this ranking table in this column for statistical significance. So we could make a visualization that shows exactly that. But for all of the comparisons being made at once, maybe to be a little more compact. Instead of having to click through each state one at a time, we can have one graph where each column of the graph is equivalent to what the column in the ranking table would look like if you clicked on a different state. So let's walk through this. On the left-hand side, we have essentially the ranking table that we had before. We have the estimated rank, the name of the state, the point estimate, and its standard error. And here, let's say we've selected Louisiana again. So here we look for Louisiana on the bottom axis, and this column is going to be white, where the difference is not statistically significantly different, and then different shades of gray for states that are significantly higher or significantly lower, where again here we've done this demi-Bonferroni correction like we talked about, in the sense that we're assuming Louisiana is the one baseline we're interested in, and we're correcting for 16 possible tests being done at the same time. If you switch your focus to a different column, you can use a different state as the baseline and then look at the comparisons for that other state versus the other 16 states. There's a question as to whether the demi-Bonferroni for just 16 comparisons or the full Bonferroni for all pairwise comparisons is more appropriate for this graph. Again, depending on the target audience, that's something to think about, but the visual form would work both ways. It's just the actual way it comes out would look a little different. So this is one visualization. The next one is one that we saw a few slides ago, but I'll reiterate it just to say this is another thing that we've implemented in the package and in the associated paper, is these confidence intervals for differences directly. So just as we were doing before, you can choose here Louisiana as a baseline, and for each state compute the confidence interval for the difference between Maryland and Louisiana, DC and Louisiana, and so forth. We are highlighting in bold the states whose estimate is significantly different, and a lighter line type for the ones that are not significantly different. All right, so here's another plot which if the previous ones raised questions, we'll see what happens with this one. So the concern that you might have about the one we talked about just a minute ago, confidence intervals for the differences directly, is that it doesn't actually show anything about the precision of Louisiana directly. It doesn't tell us how precise Louisiana's estimate is. So could we come up with something that shows both the precision of our reference state, the precision of Louisiana's estimate, and the somehow relative precisions of all the differences with Louisiana? So this is what is called a comparisons interval plot. This is based on work by Almond, Lewis, Tukey, and Yan. And we thought it was an interesting exercise to implement this, although the interpretation can be challenging, so I'm not sure that we'd recommend this for a general audience. But I'd like to go through this and sort of discuss how this compares to the plot we were just looking at. So the gray shaded area in the middle, you can see on the bottom x-axis, is exactly the confidence interval for Louisiana in this case. So for Louisiana, its confidence interval goes basically from 24 to 25 minutes mean travel time to work, and that's what's shown here. For each other state, an interval is constructed such that if that interval overlaps with Louisiana's interval, then that pair is not significantly different. If this interval doesn't overlap with Louisiana's gray shaded interval, then they are significantly different. Again, I know that wording we might tighten up a little bit. But these are not usual confidence intervals for the other states. So here on the top x-axis, we show, with the same units as below, but just with a different baseline, we show 0 at the edges from Louisiana. And you can look at the distance between Louisiana and the edge of one of these other intervals. So that distance itself, so not the actual interval being plotted, but the negative space between this strip and this other interval, that is the confidence interval for the difference between the state and Louisiana. Let me show a schematic illustration that might help. So here, let's say we have Louisiana as a reference state. Here's its point estimate, and here is its regular marginal confidence interval just for Louisiana itself. Here's another state with an estimate that is lower than Louisiana's estimate. We'd like to construct an interval with the following property. The distance between this interval's upper bound and Louisiana's lower bound is one end of the confidence interval for the difference between these estimates. The difference between the outer edges, between this guy's lower bound and this guy's upper bound, that distance is the other end of the confidence interval for the difference between them. It's a way of summarizing a lot of information on one graph, because using the upper axis and the lower axis together, you're able to read off the same information that we had on the earlier plot, with the bonus of having the information about Louisiana's precision itself. So there are arguments to be made for this presents a richer set of information than the previous plot did. On the other hand, you do have to work a little harder to get that information out of it. It's a little counterintuitive to have the sort of the negative space between intervals as the thing of interest rather than the intervals themselves. So for that reason, it's worth taking caution with this visualization, but it is one that we've seen in the literature that we thought was an interesting concept that's worth exploring, and we chose to implement it in the package as well. So there's one more slightly mathy concept to go over before we get to the final set of plots. This is an idea from a paper by Goldstein and Healy, and so we're calling these Goldstein and Healy corrections in a sense. So say that we have, again, two populations. Let's talk about concretely Louisiana and Texas, and we'd like the intervals to have the property that the actual intervals for each of those states, the Louisiana interval and the Texas interval, overlap if and only if those two estimates are significantly different from each other. One way to do that is by changing the confidence level of the marginal intervals that we're plotting. So instead of showing 90% intervals for each of the two states and then being disappointed that their overlap doesn't really correspond to significance of the difference, we could find what's the right confidence level to show. So in this case, I think it's something like 80%. If we happen to show 80% confidence intervals, then the overlap or not between those two intervals actually does correspond to a level 0.1 test of the difference between them. So this is a calculation that I haven't gone through here, but it's straightforward to do. Are both the American statistician paper that we've submitted and the research report. I think we have a 2014 research report here that goes through the calculations in more detail. But essentially, you can choose, if you'd like the test of comparing any two populations to have level alpha. So for our case, we might want level alpha equals 0.1. We can choose a alpha GH, alpha Goldstein-Healy, that is a different alpha for actually showing the confidence intervals. And when we show those confidence intervals with a correctly chosen alpha, then whether or not they overlap is actually equivalent to this test. So that works for having just two populations. If we have more than two populations, you're not guaranteed for this to work across all pairs, but something that you can do to approximate that is to say that, okay, on average, across all of the k-choose2 pairs that we're comparing, the level of all those tests on average is the target level of alpha. I know that's not entirely satisfying. It's not guaranteed to be conservative at all, but it's an alternate approach to showing everything on one slide, on one graph, with approximately the right coverage, or approximately the right level for each of those comparisons. With all that said about the Goldstein-Healy idea, when you plot it, it just looks like a usual set of confidence intervals. It looks like a bunch of marginal confidence intervals, but now they've been adjusted to be a little shorter. Each of them has a slightly lower confidence level than the usual marginal ones would, so that now you can take a particular pair, compare them for overlap, and say, well, it has this average significance level. At this average significance level of alpha, it is or it is not significantly different. And then what we realized is you can add more information to this by making what we're calling two-tiered error bars, or two-tiered confidence intervals, where the inner tier is these Goldstein-Healy adjusted versions. So you can compare overlap of the Goldstein-Healy ones by looking at the inner intervals between the vertical spikes, vertical lines, but the outer lines are the usual 90% confidence intervals. So you get both sets of information. For each state, you see its 90% confidence interval. You see the precision of that state directly, but you also have these Goldstein-Healy corrected versions, which you can, whose overlap you can compare in a legitimate way if you accept that this average confidence level is, average significance level is something that's appropriate. Or, as per the suggestion, if you do the conservative version, then you get conservative but correct testing as well. And finally, this has been so far with no Bonferroni correction. Let's say that we want to do a demi-Bonferroni correction again. You might want to do a full one instead, but here let's show the demi-Bonferroni correction. We're showing each individual confidence interval as before, the individual 90% intervals. Now we're doing Goldstein-Healy and a demi-Bonferroni correction at the same time. And what that did was made the corrected intervals become wider than the individual ones. So now the roles of which is the inner tier and which is the outer tier have flipped. So we want to label that directly on the plot to make it clear